We are ready to start. So the next talk will be my Mark Warner, who's going to speak about photo-elastomers and maybe other things.
Good morning and welcome to this next session. Before I start my talk, I'd like to make a commercial announcement. The commercial announcement is that the 7th International Liquid Crystalline Elastomer Conference will be in September in Shanghai. Shanghai is a wonderful place to visit, and I can really warmly recommend it, having been there a couple of years ago. And we have every hope of a very exciting conference about the mechanics and other optical aspects, for instance, of these interesting materials. So do think about attending, and I think even for students, there's even some sort of partial support available. So those of you who are from the iCamp and who are research students could think about this as a possibility. So I would like to talk about stress dynamics in pneumatic photoelastomers. So we're keeping with this theme of mechanics, and a rather unusual sort of mechanics I hope to show you, and a mechanics that is driven by light. And it's the light aspects that interest me particularly. This work is done with a research student at the Cavendish, Milos Knežević, who's in the audience and part of iCamp, and with Martin Čopić from Ljubljana, who's currently for an extended period in Cambridge. It draws heavily on the pneumatic solid body mechanics, which is work that I've done over many years with Eugene Terentjev, and the trace formula and various other sort of fundamentals of pneumatic mechanics was done with Eugene. And this question of nonlinear light absorption was done originally with Daniel Corbett, also in Cambridge. So I want to talk about photocontraction and pneumatic elastomers. I want to talk about an example of the importance of the dynamics of actuation by looking at a solar mechanical motor, and then talk specifically about photo-induced stress building up because we clamp the sample and we find anomalous dynamics. And this anomalous dynamics will turn out not to be because of high polymers, which is the usual source of anomalous dynamics in this complex field, but from the bleaching wave that penetrates the solid. So I'm going to talk about pneumatic elastomers. And to make an elastomer, you need polymer chains. And if these polymer chains are in a pneumatic field that is of orientational order, then they will naturally elongate. And when they're elongated, they are just changing their molecular shapes. There's no macroscopic effect. But if we cross-link chains together, they form elastomers, and elastomers are respectable solids. And this molecular shape change induced by the orientational order has an effect of giving mechanical shape change. And the mechanical shape change is essential to the interesting mechanics of these solids. And here is an example of that. It is of an elastomer, and it's in a measuring cylinder and having hot and cold air blown down the cylinder. And the molecules that, well, first of all, the pneumatic rods that are part of this pneumatic elastomer are isotropic in the high temperature state and ordered in the low temperature state. And the polymer chains, which are important to make an elastomer, a solid, are isotropic in their shape distribution at high temperatures and are anisotropic at low temperatures. And this sphere is supposed to represent the shape distribution of the chains that make up the solid. And when they are elongated, this prolate ellipsoid represents their shape distribution. They are Gaussian chains, and they have a Gaussian distribution of shapes, and this is the second moment tensor that describes this distribution. So a Gaussian's entirely defined by its second moment, and in an anisotropic Gaussian, there's a mean square length along the director and one perpendicular. So the chains are elongated here because they're in the cold state. The material is naturally long, and when we heat, it shrinks by a factor of 3 to this high temperature state. So these are large effects, and that's what makes them very interesting.
What's the suitcase going up and down on the right here?
This suitcase is actually a mini suitcase, a bulldog clip, and it's simply there to make sure that it doesn't curl up and get stuck to the sides and so on. And also to illustrate that when we heat it, we can do mechanical work by lifting a weight through a distance.
And the times are as seen in this movie?
Yeah, this is roughly speaking real time. We saw in the last talk we can have optical effects that take milliseconds or they can take hours. There's a whole range of timescales. This talk is about photo stress. So I want to talk about a situation where we induce the change from low order to high order, not by cooling, but by going from light to dark. And we have actually seen this particular slide many times. The way to change pneumatic order is not only by heating and cooling, but if we have a set of pneumatic rods which order orientationally, and some of the guests are rods with a bendable unit at their center, then if we absorb photons into this bendable unit, in this way here, this central element is this azo group. If we absorb a photon into this group, it bends. And so the guests bend, and being bent and long like this, they destroy the pneumatic order of their hosts. And so the whole system is in the isotropic state on absorbing a UV photon. And then we can have a thermal decay back to the ground state, or we can shine light of a different color to induce the isotropic state of the sample. So wherever we've seen heat before, we can think of photons, and this is the recovery in the dark. So I've tried to.
Is the wavelengths 465 and 365?
Yeah.
So you change the wavelengths that you provided?
That's right. So you shine light of a different color if you want to recover. And if you have a different dye, then these wavelengths will be different according to the chemical structure of the dye.
There's no tendency of the bent ones to phase separate from the straight ones?
Yes, there is. If you had a liquid of these, then they will have a lower density, will rise to the top, and you have beautiful optically induced convection phenomena. Very, very beautiful. These will be part of a network of chains in an elastomer, and they cannot phase separate.
The fact that they're an elastomer,
Yeah.
you don't have to worry about that.
Absolutely.
Sorry, I missed. If you switch on green UV and it goes to that. If you don't, if you just let it go, it decays by itself also.
That's right, thermally. So there's an
Temperature also.
yeah.
Sorry.
So this excited state goes to the ground state with a time constant that may vary from milliseconds to hours, depending on the chemical structure. Right. So I'm going to be interested in cantilevers. And here's a cantilever, and to define my notation, it's of thickness D. So here's a cantilever, and it's of thickness D through its section. And this is a particular example from Peter Porphy, who's in the audience, and he is shining a light on it, so it hits here, and there's a differential absorption through the thickness, a greater contraction at the front face than at the back face, and therefore the system bends, as we heard in the last talk. And I can show a picture of that. So the light pulse comes in, causes a contraction on this front face, and in this particular example, the contraction takes place over, I don't know, is it 40 milliseconds or thereabouts?
It's less than that.
Less than that, yeah. And then there's a rather slower recovery, as in the dark in this case.
And that's the recovery just due to spontaneous straightening out.
That's the spontaneous thing. Now, there's some debate sometimes whether this is just due to a pulse of heat being delivered preferentially at the front face, and that can be the case sometimes. But if you take a polydomain sample and shine polarized light on it, then you see a contraction in the direction of the plane of polarization of light. And it's quite noticeable. You rotate that plane, then you get contraction in a different direction, and it's clearly an optical effect there and not a thermal one, because the domains are extremely small, and if it were thermal, you would get heat transferred from one domain to another. It would be like heating a polydomain sample. There's no broken symmetry of the direction. So let's think about light, although it can be argued that sometimes it's heat. And I'm going to talk about a system which is clamped. So I'm going to take this cantilever, grip it at the top and the bottom, seen in section, it's of thickness D, and I'm going to shine light in the side of incident intensity I0 and try and look at the stress rising because you don't allow for the contraction. So that's the rest of this talk. Now, why would I want to do this? Well, here's an example of what we might call a motor, and it consists of two wheels of different radii, and connected around these wheels is a band of liquid crystal photoelastomer, which goes right around. The two wheels are constrained to turn at the same angular speed because there's an inextensible band connecting these inner radii. And we will take this band, and everywhere from here all the way around to here, where the red arrows are shown, we will either heat it or we will illuminate it to cause a contraction. And everywhere from where it enters the second wheels and right around to here, it will cool down, the heat comes out, or it's in the dark and we're allowing for the length to increase. And you can see that there's a greater force on this side than on this side, and therefore there's a net torque on this wheel. There's, of course, the opposite, an oppositely directed torque on this wheel, but this torque is smaller because the radii are smaller. So overall, there's a net torque on the system which will cause it to rotate in this direction. And if I connect a weight to it here, I have a way of doing work on an external sink. So it's a way of turning the light energy, which appears around this side, into mechanical work. Now, the first thing to notice is that this band is in contact, non-sliding contact with the wheel all the way around till here. So where it is receiving light, its natural length decreases, its actual strain doesn't change because it's in contact with the wheel, so there's a big tension arises, and it's only here does it become free, establish a new equilibrium stretch, and the tension is realized. So that's like one of these clamped systems, in fact.
Do you have any of that slip?
Well, these things tend to have non-sliding contact on surfaces. That's why I had the weight on the thing in the measuring cylinder, because if it stuck to the walls, then it might not go up and down. But yeah, one could maybe make the surface rough so it won't slide. Yes?
The kinematic incompatibility between the two wheels at the center turning in the same rate?
How do you mean? I mean, this is just a rigid connection between the two. So there'll be forces in this band here to make sure that the wheels don't turn at different rates. If you liked, you could have a clockwork mechanism with cogs so that they're constrained. Yes?
What direction it will go? Clockwise or?
It will go clockwise.
Why?
Because the force on this side is greater than on the force on this side. This is cold, and therefore it's naturally long, and this is hot or illuminated, and it's naturally short. So there's a great tension builds up on this side than on this side. So I'm now going to retreat from the motor and actually talk about the underlying physical phenomena that interest me. And way back in 2002, Terentiev did a rather clever experiment. He clamped this sort of sample so that when there was a natural contraction, he could separate the dynamics of the movement of the chains from actually the other dynamical processes going on. So first of all, he didn't clamp it. He just measured the length of this sample as a function of temperature. So he finds that as he cools, the length of the sample grows, in this case, by about 50%. Likewise, if he then starts here and heats, then there's a shrinkage of the chain by about 30%. So then he takes this system, this strip of rubber, and he clamps it, and then he illuminates it. And this is the time after he switches the light on, and he finds a contractile stress, because when it's clamped, it can't get shorter. And if its natural length is diminished, then there has to be a stress associated with holding the ends apart. And at the same time, he measured the birefringence of the rubber strip, and he discovered that both changed in exactly the same way, which suggested to him that the underlying process of stress buildup is actually limited by the rate at which you can bend these rods and therefore change the pneumatic order. So the dynamics comes from the dynamics of the die population if you clamp it. And so you can take the stress and the stress that's built up, normalize it by the maximum stress that you'd get at long times, and so it should go up to 1. And as you switch on the light, then you find that the stress rises. And in 2011, Heino Finkelman and Sanchez Ferrer did a similar sort of experiment, and then they fitted their rise in the normalized stress to this stretched exponential. And the usual motivation for fitting to a stretched exponential is that you have high polymers, which are long chains, they have lots of internal modes, and as they move, you superpose these modes together, and you get a rather strange non-analytic form where beta can be 0.5 or 0.6 or so. But of course, the high polymer dynamics can't be related to this phenomenon because the polymers are clamped. And we know that the dynamics such as there is not due to the polymer motion because the rubber strip is clamped. It must be from the die, changes in the die. There's another reason, and that is that if beta is less than 1, the slope of this function is infinite at 0 time. And that would mean we'd have to deliver photons to create this effect at an infinite rate. And we have a finite beam. The other problem is that at long times, this doesn't go on to this saturated form quickly enough. So my problem for the rest of this talk is to explain this phenomenon. At this point, I have to make a slight apology for the ICAMP people. They have come into the tail end of a maths conference, and for a lot of us, the interest in this subject is in the nice equations that arise. And so there will be some equations from now on, for which I can't apologize terribly much, but I just mention this. Right, so I want to try and explain the buildup of this stress, and in particular the dynamics of the buildup of this, since it will determine the efficiency of this motor that I've talked about, and so it's quite important. Now, the free energy density of a pneumatic elastomer depends on the free energy density of the pneumatic liquid that it's really made up out of, plus a contribution which is due to the elasticity. Now, for elastomers, you can prove that it separates in this additive way. It's not obvious, but it can be shown. And lambda is going to be the strain tensor. So we're going to talk about a very simple form of the strain tensor, which has got principal stretch as lambda and 1 upon root lambda. So to address a question before, this Poisson ratio is a half, and it's because it's a rubber. So it's incompressible, exactly. What it means is that the energy scale, which is the shear modulus for the elastic part, is 10 to the 4 times smaller than the bulk modulus. So all deformations have to occur at constant volume. So we're going to deal with a system. Let me jump ahead for a moment. Imagine a cube of rubber, 1 by 1 by 1 in its 3 dimensions, and it's changing shape by a factor of lambda along the director. Then it has to change shape by a factor of 1 upon root lambda in the 2 perpendicular directions. So if I multiply these 3 dimensions together, instead of 1 by 1 by 1, which is 1 cubed, I have lambda times 1 upon root lambda times 1 upon root lambda, which is 1. Now, the second remark is that the pneumatic energy is much higher than the rubber elastic energy. because the pneumatic energy is of the order of kBt per rod, and the elastic energy is of the order of kBt per strand. And there may be 50 rods for every strand. So we will take this to be much smaller. And so what we will do is take the Q to be the Q that minimizes the pneumatic free energy, and it just sits in here determining the elastic free energy. And this is this formula for the elastic free energy that those of us who have been here all week will have heard several times referred to as the trace formula. And what it says is that the energy density is the shear modulus, which sets an energy scale for an elastomer, and it depends on the square of the distortions or the stretches. But unlike a classical elastomer, it has squeezed into it a memory of the initial shape distribution of the chains and the inverse of the shape distribution or the gyration tensor currently. So the naught says what happens at the start when we form this material, and without the naught, it means it's the current shape distribution of the chains. And I'm going to take a very simple form for the distortion tensor, this here, which just consists of the stretch along one direction and these contractions along the other direction. The parallel direction has lambda parallel squared, which is just lambda squared, taking this value for it. The perpendicular directions have lambda perpendicular squared, which is just 1 upon root lambda squared. And there are two perpendicular directions, which is that 2 there. And I have the ratio of this parallel length of the distribution initially divided by the parallel length of this distribution currently. So these are the anisotropies of the polymer distribution that makes up the rubber. Well, we've seen this before. In the case of the Terentiev experiment, he started off with a spherical distribution, so this number and this number are both 1, and then he had elongations along the field and contractions perpendicular to the field of this distribution of chains. And if you take this expression and minimize it, the minimum is not at lambda is equal to 1, which is a sort of ordinary solid at rest, unchanging in its shape. It changes by, it turns out, the cube root of the ratio of these two numbers. And we saw in Terentiev's case, this cube root was 4 or 3, which means that these anisotropies must have been something like 60 or so. Cube root of 60 is 4.
So you think of the ratios of these L, so these L's are changing not because of the elastic stress, but because of the photoillumination.
Yeah.
And so that's just contained in the geometry and the
Yeah.
chemistry of that process.
I must investigate that now. That is my task, to try and specify how these distributions of the chains are influenced by the underlying pneumatic order. That is the whole problem now, as you identify. And we're going to deal with a situation where this thing is initially long, and we're going to illuminate it so that the anisotropy changes to this photo value P here, and this will cause a contraction because we'll illuminate it, this will become more spherical, and the system will contract. But before I do that, I'll actually compute the stress. The stress, the true stress in this case is just dF by d lambda, that's the free energy density, multiplied by lambda to correct for the fact that the cross-sectional area would be changing. And I'm going to compute the stress in the system that's suffered a photocontraction. So I'm going to say this thing has contracted by this much. So it's, in this case, it's starting in the long state and contracting. And so I'm going to have this formula with this lambda put in to account for the fact that it's contracted. And then once it's contracted, I'm going to stretch it again back to the length determined by the clamps. So let me just do that. If I'm in the contracted state, and I then try and re-stretch it by a factor of lambda, then it turns out that the stress, which is related to the derivative of the free energy density, is just lambda squared minus 1 upon lambda, with this number out the front, which just accounts for the energy state in the contracted form of the elastomer. And depends on the initial elongated state here, and this is this photo state, which is more isotropic. Now, how much do I have to stretch this to get it back to the clamps? I have to stretch it by the inverse of the contraction that it just suffered. So if it contracted by a factor of lambda ps, which is less than 1, then I will stretch it by a factor of 1 upon lambda ps. I get back to where I started. So I've put this factor in, and it sits here. And if I then use these results here, and this is what this photo contraction was, then I get this really simple expression for the stress, which is just the shear modulus into the ratio of these changes of the shapes of the polymers, parallel and perpendicular to the director. So it's an innocent expression, but I've still not addressed John's question, well, how do these things vary with the pneumatic state of the system? And to do that, I have to introduce a model. And the simplest model of a polymer is that it's made up of a whole lot of links which are freely jointed. So if I start at one end of the polymer, there's a chemical rod here which is of length A, shall we say, and then it just consists of a whole lot of bonds of equal length, and they're freely jointed. In other words, there's no correlation between this direction and this direction. These rods just correlate with the pneumatic field. So if this is N, there's some angle that they make with the pneumatic field. And that's the important thing. It's the pneumatic field which will give these rods a bias. And if you then say, well, the projection of the rod onto the director is cosine theta, and I'm interested in the square of that projection because I want the mean square length of the chains, then I end up with averages of cos squared theta, and the order parameter Q depends on cos squared theta. So you can take it as given or derive it yourself that the step lengths are just given by some fundamental length A, which defines the length of these bonds, into 1 plus 2Q along the director and 1 minus Q perpendicular to the director. So in the state of perfect pneumatic order, these rods would just be up or down like this, and they would have no lateral extent in this crude model, and so there would be no sideways dimension to this distribution of chains.
The normalization of this is that if you have perfect order, the Qij tensor is just Nij minus 1/3 delta ij?
Yeah.
Yeah.
And less than that,
So
if
Q is 1.
Q is 1 in the state of perfect order. So we have a factor of 3 going up this axis and 0 going across. And if I illuminate it, then I lower the order parameter, which you might think is equivalent to just raising the temperature. So that these in the illuminated state are equivalent to being at a higher temperature, they're more isotropic. And that's the whole effect, that if it's more isotropic, it will want to shrink, and that's what I'm trying to calculate.
Does it make a difference that these systems are, when you shine the light and keep the light on, it's actually a pump system rather than merely a deformed system?
Yeah.
Does it ever matter in these systems?
Yeah, it will matter, because you won't then retreat back to the ordered state.
Not only, but it's also actually driven. In principle, it's actually driven if you're continuously shining.
Yeah, sure. So it's like an active system.
Yeah,
perhaps.
yeah. Just wondering.
To make some contact with the other program, yes. I'll go on to those dynamics, because the driving is awfully important. But let me try and map this problem onto temperature. If I have a distribution of rods and they have an angle theta, then they will suffer a mean field which from the rest of the rods to try and make them aligned. And this mean field in a liquid crystal is some minus that says it wants to be along the director, a coupling constant J times the mean order that it's seeing of the other rods times this angular factor P2 of cos theta, which says that it wants to be along the ordering direction. And if I take the view that the coupling to the other rods depends on how many other rods there are locally, then if I then reduce the number of other rods because some of them are bent and don't add to the ordering effect, then I say that the coupling is some fundamental value when it's in the dark minus or times 1 minus the number of neighbors that are bent. And the number of neighbors that are bent are the number fraction, or the fraction of neighbors that are bent is the number fraction of molecules that are dyes times the fraction of those that are in the bent state. So let me retrieve this. If I have a dye molecule and it's straight, that's in the trans state. And you recall the bent molecules are in the cis state. So that the fraction that are in the cis state is some number now greater than 0, limited by 1. You can't have more than all of them in the cis state. And the number of dye molecules, we don't want too many. We want about between 2 and 5%. Otherwise, we just absorb all the light, and it's much more than is needed to get to the isotropic state. So if I rearrange this formula here, I can make the change in the strength of the coupling sit with the temperature, and I can say that the effective temperature is the real temperature divided by this factor 1 minus NC times delta, which you can see is a rise in the temperature. Because delta is small, I can always expand this up, and so I can get that the temperature is increased by a factor which is proportional to the number fraction of bent molecules. So I'm going to say that the number of molecules, the number fraction is NT plus NC is equal to 1. So what I need is the order parameter, and the order parameter is a function of temperature. And into this temperature here, the T effective, I can say it's the real temperature raised by this factor here. And I can take these order parameters and expand them out to count for this change in temperature. And if I do that, I get the stress is proportional to the energy scale, the shear modulus, a constant B, which says how quickly the step lengths vary with changes in the order parameter, and how quickly the order parameter changes with a change in temperature, and then the essential part of the temperature change appears here, the cis concentration. So I can say that the stress due to the change of the order parameter is actually this constant out the front times the cis concentration of dye molecules. So it's a very it's a powerful result in some sense, because it says I can relate the mechanical properties, the stress, just to the change in the relative population of bent to straight guests. So now I've solved that problem of how the stress depends on the change of the order parameter, but now I have to work out how the change of the cis concentration, the bent dyes, is determined as a function of depth and time as a result of illumination.
So doesn't this depend on how fast Q varies with temperature, or is that?
Absolutely. So this B subsumes dq by dt from expanding out the variation. There's a lot of stuff buried in B, but it's a constant. Well, it depends on temperature, but it doesn't depend on illumination. Or position. Right, so now I want to talk about how the order changes, and to do that I have to describe how the light enters the body. So we have a beam that's entering the body. Here's a cartoon of it, and it has an intensity inside I of x, actually I of x and t in general. And I changes with depth, like di by dx is proportional to minus I, and that's the standard Beer's law. di by dx is proportional to minus I. It depends on a rate coefficient of absorption. It depends on the energy per photon, because we're looking at the change of the intensity, and the number of dye molecules per unit volume. And it depends on the number fraction of trans, because the trans do the absorption. And I can subsume, well, first of all, I'll divide the intensity by the incident intensity, so I have a normalized intensity. And I will subsume, I will write these constants gamma and gamma as 1 upon dB, which is the Beer length. Then I have a rather simple looking equation, di by dx is equal to minus I nt over dB. And if nt is 1, so I haven't changed the dye population, then I have a simple absorption process, and I have e to the minus x over dB, the Beer length, which I've summarized here for reference. However, this factor, the number fraction of trans molecules that are doing the absorption, well, I should first of all break at this point and say there is absorption by the cis molecules. And that absorption is quite important. It actually depletes the beam, and it will also affect the back dynamics. And in this simple development, I haven't put that in explicitly. But as Martin Choppage, when he first came to Cambridge this time, pointed out, it's actually absolutely vital. And this is something I'll say a bit about at the end. So if I look at this equation, I see that nt is actually a function of x and t. So I can't actually just integrate this to give me a simple exponential. I must look at how the dye population is driven to the cis state by the absorption. So the rate of change of the trans population is proportional to the rate at which we have this absorption process times a quantum efficiency, which says how likely each absorption is to lead to the cis state and not just keep it in the trans state. It's number of order 0.8 or thereabouts. And the trans population is restored by the decay of the cis population thermally, or we could do it optically, which is this bit that I haven't put in. And if I look at this at equilibrium by setting dn by dt is equal to 0, then I find that the trans number fraction is 1 over 1 plus alpha I.
Thermal relaxation here.
That's, yeah.
Optical induced thermal relaxation.
No, this is the thermal one. The optical one is in here, and I haven't, I mean, you can write that down, and you should, but it's more complicated for the mathematics. And this factor of alpha is just subsuming these constants together, and also it's a measure of the incident intensity. High alpha is high incident intensity. And I can then put this into this equation, and it's now a nonlinear equation, and the solution of this equation is this for the intensity as I go through the thickness of this cantilever. And the solution is at short times, when all the dye molecules are present, the absorption is high, and we have this Beer's law. And at long times, right out here, shall we say, the variation is linear. So we have very deep penetration here of the order of 30 or 40 Beer lengths, which in an exponential case would certainly be well zero by that time. And I now have it. I can have the stress as a function of depth, but I'd also like the dynamics. So let me go back to these dynamical equations.
So would it fair to say the physics of this, that you're bleaching out the things that absorb the light, so it's penetrating further and further as time goes on?
Yeah, so the question is the physics. We're bleaching out the absorbers, and so that light can get in more deeply and affect the molecules further into the solid. Exactly that.
And that'll go on forever? If you had an infinite sample and you kept illuminating, would it keep penetrating further and further?
No, the infinite limit is essentially this one here. It says that there is some back reaction, and so you can't completely kill the trans population because it's replenishing itself. The slower it replenishes itself compared with the incident intensity, the deeper this penetration will be. And that is the significance of this parameter alpha, that balance that you were talking about. I'll come back to that graph in a moment. So now I've got my dynamical equation, which I solved in the static limit, and I'm going to rewrite that by multiplying through by tau, the thermal back reaction time, and that clearly sets the timescale for t. And I've got all of the rest of these factors as before. I have a pair of nonlinear coupled partial differential equations, and I can reduce those in this simple case, at least, without the optical back reaction to a simple quadrature. And the quadrature is in terms of this absorption, which is minus the log of this intensity. And the absorption is the vital thing in light. So now I'm back to this diagram, and I go from Beer to the long, the deep linear penetration by a bleaching wave which goes through the solid, which is this wave of conversion of trans to cis, where I've depleted the population. So there's an interesting dynamics associated with that penetration, and that is what I'm alleging is the stress. So in the remaining minute or so, this is my absorption equation, true at all times and all depths, and I can rearrange this equation so I get the cis concentration, because that was what determined the stress. And so it's just in terms of the Beer length, the derivative, the logarithmic derivative plus 1. If I want the force on the clamps, it's the integration of the stress through the thickness. There's more stress from the front face than the back face. That's what gave bending when it wasn't clamped. And this was the stress formula, which just depended on the cis concentration. So if I integrate the stress formula, I'm just integrating the cis concentration. And that's an easy equation to integrate because this is just a logarithmic derivative. And the result is the thickness plus the Beer length times log I. And that's the thickness minus the Beer length times the absorption. So it says that the force on this clamped object is just actually proportional to the absorbance, the optical absorbance. And if I take the Beer form, which came about because I didn't transform anything, I just had all the absorbers there, then nothing has changed and the result is 0. If we don't convert some of these to a bent form, we don't generate any stress. And I can normalize this by its long time value, which gets rid of this nasty or involved coefficient. And I have a simple expression for the normalized stress, that is the force, as a function of time. And it's a simple expression which just depends on the buildup of the absorption divided and with the long time absorption in the denominator. So the dynamics of the force is the dynamics of the bleaching wave. And if we take this formula with the optical back reaction injected into it, we find essentially a perfect fit to the data, which gives us some confidence that this unusual mechanical dynamics is purely optical in origin. Now, it would be much easier to fit to experiment in the future if these fundamental things controlling light absorption were measured at the same time. So that would be our proposal for future experiments. Measure the Beer length, measure the dynamics of the decay of the photostate, and measure the penetration, the deep penetration of light when you have intense beams. We have fitted this by fitting these 3 parameters. But there should be no parameters, ideally, if you measure those independently. So let me conclude. To get force, you need a deep penetration of the radiation. It's no use just illuminating a thin skin on the surface. You need to convert a finite proportion of the absorbers. If you do that, then you have nonlinear absorption. And the consequence of nonlinear absorption is a non-trivial dynamics. And with that, I'll conclude. Thank you.
Thank you very much. There's time for questions.
I didn't understand your answer to the question about whether it went round clockwise or anti-clockwise. Because I don't think you can just argue in terms of tension, can you?
No, you've got to argue in terms of torque. So let me return to the motor. This wasn't to be a talk about motors, actually, but it seemed to have interested people. You agree that if this tension is larger than this tension, there's a net torque on this wheel, that way? No. Why not?
force on one and on the other. F2 R2 minus F1 R2 is greater than 0.
No. The lever arm here is R2, and the lever arm here is R2. So the net torque, T2, shall we say, is F2 minus F1 into R2. So there's a net torque on this wheel this way. But that's not the end of the story. There's a net torque on this wheel, which is the other way. And you would worry about that because the two are rigidly connected with each other. But all that does is convey a torque from this one to this one, which is opposite and of magnitude F2R1 minus F1R1. And that's smaller because R1 is smaller than R2. And therefore it has to turn. Siram had a...
Yes.
So I don't know, maybe this question is a little outside what you're talking about, but are there situations where instead of merely inducing a transition, you have objects that have a photocycle? So you just keep the light on, and it pumps, like bacterial rhodopsin or something. So, you know, and so merely keeping the light on drives a motor.
Well, that would be the ideal, actually.
Are
I
there
don't know of
candidates?
such a system. There's a man in the audience who probably does, but...
I mean, it's just transfer reaction. It's continuously ongoing. I mean, you excite the molecule, dense, but it also goes back to blood.
True, but
so you have to pump it, yeah?
But
and the higher intensity you are using, the more higher you're populating the system state.
No, but I was wondering if there was something slightly where there was something with, say, 3 states, and as exists in some light harvesting objects like bacterial rhodopsin or something, where it actually goes from one to the other and then comes back by a different route. So the molecule in question goes through a cycle, and then that can drive motor-like action in the system. Anyway.
I'm not sure I would welcome that for this sort of idea, because the back cycle would be taking it back to the elongated state, and I only want that to happen after all the action's finished, after it goes onto this wheel. So, but I think it's a very good general point. Can one make active solids, pneumatic or smectic, is very interesting, in the sense that you guys are working on them. That's something I would like to explore.
I just wanted to ask if there's a simple analytic form for the final time dependence of the stress that you get, or if it's just comes from numerically inverting an implicit equation.
Well, the form is given by this equation here, in a sense, and that's not a nice analytic form. It's an implicit form. I get A of T and X from...
Right. Does it have any simple asymptotics? I mean, at very large time, how does it approach this limit? Can you say anything about that?
Yes. Martin is nodding.
If you take tau equal to 0, then
Martin.
if you take the relaxation rate to be very slow, then you get Fermi function, exact.
The assumption you use of deformation at constant volume, I was just wondering, so that's pretty for rubber. How good is it for a pneumatic elastomer? I mean, you'd expect some small change in volume. Is it 1%, less than 0.1%?
It's the sort of volume change that you have when you go from the pneumatic to isotropic state in a conventional liquid pneumatic. And that's known to be about 4 parts in 1,000 or something like that. So there is a tiny effect, but it's very small.
But you're not even going to the isotropic state. You're just going between 2 slightly different pneumatics.
Well, yeah, the remark was I'm not even going to the isotropic state, but I would like to go to the isotropic state because I get the full stroke of this. This Terentiev experiment was going to the isotropic state. He gets 300%. So yes. Another question down here.
Yes,
Oh, sorry.
Final propagation speed.
Yep.
But what you did,
Just 1D modeling, uniaxial move.
Yes.
may I ask you to show me the intensity gradient vector direction and the normal stress direction in this?
So this is a clamp system. So we will have a stress which is greater as we at the surface than as we go in like that.
And intensity gradient?
And the intensity gradient of the light, you mean?
Yes.
The light intensity gradient is exactly this. So at a given time, as I go in, depending on where the thickness of the sample is, I will have this variation of the intensity of light. And then the stress this way, well, the sample is thin, and the surface tractions are 0, and so within the normal approximations, for instance, of beam bending theory, you say that the stresses this way are 0.
From elasticity theory point of view, plane stress.
Yeah,
Plane
yeah,
stress.
yeah, exactly.
Any further questions? Okay, if not, let's thank Mark again. I have to make a couple of announcements. So I would like to ask Mark to hand the microphone